Hello everyone. Today we'll be discussing the Shor's algorithm. Shor's algorithm is a polynomial time quantum computer algorithm for integer factorization. Informally, it solves the following problem. Given an integer, find its prime factors. It was invented in 1994 by the American mathematician Peter Shor. But before we dive into the algorithm, let's discuss a real-life application that motivated its study. RSA cryptography is built on the principles of public key exchange and the computationally difficult problem of prime factorization. It takes plain text from the sender, encrypts it into ciphertext, which then gets decrypted back to plain text and is sent to the receiver. RSA cryptography is based on the principle that while it's really easy for a computer to take two large numbers and find their product, it's not so easy to do it the other way around. It's not so easy for a computer to take a really big number and decompose it into its prime factors. RSA cryptography primarily uses these prime factors as keys for encryption. So if you ever wanted to break RSA cryptography, all you have to do is find these prime factors. But the question is, how do we factor a really large number? And by really large, we mean a number that's over 100 digits long. In order to understand the algorithm, we must know what modular arithmetic is. We say that two integers a and b are congruence modulo n if and only if they have the same remainder when divided by n. We can use this knowledge to make an important observation. Look at the powers of 4 mod 7. 4 to the 1 is 4 mod 7, 4 to the 2 mod 7 is 2, 4 to the 3 mod 7 is 1, 4 to the 4 mod 7 is 4 again, 4 to the 5 mod 7 is 2, and 4 to the 6 mod 7 is 1 again. If you look carefully, you will see a repeating pattern. 4 2 1, 4 2 1, and this pattern always ends in 1. The length of this repeating pattern is what we call the period, an important concept that we will get to in a minute. But before that, what is so special about the numbers 4 and 7 that we get this repeating pattern in the first place? The answer is these numbers are relatively prime. That is, they do not share any common factors other than 1. Now let's go back to the idea of the period. The period of the repeating pattern is important because if the period of x mod n is r, then r is the smallest number such that x to the r is congruent to 1 mod n. We now have all the prerequisite math knowledge in order to understand the Shor's algorithm.
Now, Shor's algorithm, we're trying to find p and q that are factors of n. And for a reminder for future steps, you have to remember that Shor's algorithm is a probabilistic algorithm. And so for the first step, when we pick any number a smaller than n, a is going to be our first attempt. And if it gets us a factor of n, then great. If it doesn't, then we're going to have to go back to this step and then pick a different random value of n, a smaller than n. For a second step, we'll have to compute the period of r of a mod n. And that will be done by calculating a mod n, a to the 2 mod n, a to the 3 mod n, so on and so forth, until we get a value of r that's an exponent of a, such that it fulfills the definition of period r of a mod n. Now, once we have the value r, we have a to the r and 1 mod n. And in congruence modulo, we're going to subtract 1 from both sides to have a to the r minus 1 mod n to be 0. Now, in congruence modulo, this means that a to the r minus 1 is a multiple of n. So that means that we can place a to the r minus 1 in an equation like the following: a to the r minus 1 equals some multiple of n, k to the n, such that k is some integer. Okay? Now, if r is an even number, we can perform the next step. If not, we're going to have to go back to the first step and pick a different value for a. If it is even, we can split a to the r minus 1 into two separate components by a difference of squares. So we can have a to the r over 2 minus 1 and a to the r over 2 plus 1 equal k to the n. Now, given that it's a product of two numbers that equals n, that means that we have the two numbers must have some common divisor with n that would include some factors such as p and q. Now, before we go on to the next step, we have to consider two conditions. These two conditions are if r is odd or if a to the r over 2 plus 1 mod n is 0. If r is odd, we can't perform the difference of squares, and therefore we have to go back to our first step and pick a different a, which is going to give us a different r. And for a to r over 2 plus 1 mod n can't be 0. Well, you might ask why. Well, it's because in congruence module, like we mentioned before, a to r over 2 plus 1 would be a multiple of n. But when we perform greatest common divisor on a to the r over 2 plus 1 and n, it's going to give us n for sure, because the first is a multiple of the second number. So we're going to have to go back to this first step and pick a different a that would get us a smaller value for a to the r over 2 plus 1. Now, since we've established these two conditions, we know for sure a to the r over 2 plus and minus 1 are definitely smaller than n, meaning that their factors must be common factors with n. And therefore, we're going to set two different factors, p and q. P being the greatest common denominator with a to the r over 2 minus 1 and n, which is one factor of n, and the second factor to be q, greatest common denominator of a to the r over 2 plus 1 smaller and n, which is going to give us two factors of n, like Shor's algorithm promised. But however, did we really break RSA cryptography? Well, not exactly, because this algorithm, first of all, is probabilistic. It's going to take us multiple tries before we get the correct values of a to the r and get the factors of n. Second of all, computing the period r mod a mod n is going to take an exponentially long time, since we have to perform a mod n, a to 2 mod n several times for one value of a till we find period r. And such a step would take us millions and millions of calculations, which can take up to years of calculation in classical computers, which is very inefficient and does not really break RSA cryptography, since it takes way too long. However, with advanced technology in quantum computers, since quantum computers can perform different calculations simultaneously using superposition states, we can cut down the time much more significantly this way. And therefore, Shor's algorithm would really shine through in quantum computers. And thus, now you have some fundamentals knowing how Shor's algorithm works in classical computers and have a glimpse of quantum computers. Thank you.